Welcome to a new deep dive. Today, we're really digging into a common challenge you hit when working with sorted data.
Yeah, it comes up a lot in computer science, data analysis,
Yeah.
basically anywhere you have ordered lists.
We're talking about finding things, but not just if they're present. We want to know precisely where a group of identical items starts or finishes.
Exactly. Think about, a standard binary search, super fast for finding if a value's there.
Right.
But what if you have duplicates? Let's say scores in a sorted list. You don't just want to know if someone got a 95. You might need the first student who got a 95 or the last one.
And that's the core problem. We're looking at material today from Hello Algo. They tackle this head on, calling it binary search boundaries. It's a pretty smart way to think about extending binary search.
Yeah, and what I find interesting is their angle. They often show how you don't need a totally new complex search just for these boundaries. You can actually leverage a version you might already know,
Which is?
the binary search that finds an insertion point.
Okay, let's unpack this. So the mission for today's deep dive is to really get our heads around finding these boundaries, the leftmost and rightmost occurrences of a target value in a sorted array, even with duplicates. We're going to use the techniques from the source.
We want you to understand this well enough that it really sticks.
Let's start with the left boundary then, the problem. Find the index of the very first time our target value appears.
And importantly, if it's not there at all, signal that. Maybe return make a one, that's pretty standard.
So how does the source guide us to that first spot?
Okay, here's where it gets quite clever. Hello Algo basically frames finding the leftmost target as being the same problem as finding the insertion point for that target.
An insertion point,
Right.
right. For a value, say, x in a sorted array, that's the index where x would go to keep it sorted.
Exactly.
And if x is already in the array, the standard insertion logic usually lands on the first spot, where an element is greater than or equal to x.
Precisely. So the insight is that if you use a standard binary search insertion function and look for your target, the index it returns is the first place that target could go.
Which, if the target exists, would be the index of the first one.
That's the idea. You trust the insertion function to do that heavy lifting.
Okay, so the approach hinges on having this binary search insertion function ready to go. Once you run that, you get a potential index, let's call it E, but you're not done, right? You need to check it.
Right. A couple of quick checks are needed to be absolutely sure I points to the leftmost target.
What's the first check?
First, you just got to make sure I is actually in the array. Like, is it a valid index if I happens to be equal to the length of the array?
Meaning the insertion point is after the last element.
Exactly. That tells you the target wasn't found within the existing elements.
Makes sense. If it goes after everything, it wasn't in the list to begin with. What's the second check?
Okay, so let's say I is a valid index, so I is less than the length. You still need to check if the value at that spot num_sci is actually your target. Because the insertion point logic might land you at the first element that's greater than your target if the target itself isn't present.
I see. So num_sci might not be target.
Right, it could be the next bigger thing. So if num_sci doesn't equal target, it means the target wasn't found.
Got it. So recap. If phi is out of bounds,
Yeah.
equal to the array length, or if phi is in bounds, but num_sci isn't the target.
Then the target wasn't really there. The source says return -1 in that case.
But if I is a valid index, and num_sci does match the target.
Bingo. Then, according to the source, I is your answer. It's the index of the leftmost target. Return I.
That feels cleaner somehow. Instead of fiddling with pointer logic inside the binary search loop trying to stop at the first match, you use a standard insertion search and just validate the result.
It really does simplify the thinking, I find. You're building on something potentially already understood or available.
Okay, that covers the left boundary. Find the insertion point for target, then validate. Makes intuitive sense. But the rightmost boundary, finding the last occurrence, that feels like it might be trickier.
It can seem that way. The source does mention, briefly, that yeah, you could try to modify the binary search loop itself.
How so?
Well, when you find a match, num_zim equals target, instead of stopping or searching left, you'd somehow force the search to continue to the right, hoping to find more matches.
But that sounds prone to errors, easy to overshoot or get stuck. And the source doesn't really detail that method.
No, it doesn't dwell on it. Instead, it offers two alternative methods, and these really stick with the theme of using the insertion point idea, which I think gives those aha moments.
All right, let's hear method 1 for the right boundary.
Okay, this first one is, I think, quite elegant because it reuses the exact same logic we just discussed for the left boundary.
Wait, hang on. How does finding the first instance help find the last instance?
You change the question slightly. To find the rightmost target, you use your left boundary finding function, but you ask it to find the leftmost occurrence of target plus 1.
Target plus 1. Okay, let me think. Why plus 1?
Consider what finding the leftmost target plus 1 gives you. In a sorted array, the index I it returns will be the very first position where an element is strictly greater than your original target.
Ah, right. Because everything before that index has to be less than or equal to target.
Exactly. So think about the element just before index I. That's index I1. That element must be the last one in the array that's less than or equal to target.
Fine. If our target value is actually in the array, that element at I1 will be the very last target.
Okay.
That clicks. That's clever.
It really is. So the process is, run your leftmost boundary search, which we know uses insertion logic, but search for target plus 1. Let's say it gives you index I. Your candidate for the rightmost target is then j equals I1.
But again, we need to validate j, right? Similar check.
Similar, but slightly different logic. First, you need to check if j is even valid. What if the search for target plus 1 return I equals 0?
If I was 0, then j would be neg is 1. That would mean everything in the array was already target plus 1 or bigger. Or maybe the array was empty.
Right. If j is manage 1, it essentially means no elements less than or equal to target were found just before the insertion point of target plus 1. So your original target probably wasn't there.
Okay, so check if j is minus 1. What else?
If j is a valid index, so j equals 0, you still have that final check.
Right.
Is the element at nems sj actually equal to your original target?
Why wouldn't it be?
Because j points to the last element less than or equal to target. It could be an element that's just less than target if target itself wasn't present.
I see. So nums sj must specifically equal target.
Correct. So the validation is if j is manish 1, or if j is valid but nums j is not equal to target, then the rightmost target wasn't found. Return manish 1.
Otherwise?
Otherwise, j is your index for the rightmost target. Return j.
Wow. That's really neat.
Yeah.
You completely avoid custom right boundary logic by just asking the left boundary logic a slightly different question. Target plus 1.
It's a great example of problem transformation. Reuse the code, just change the input and how you interpret the output.
Okay. Method 1. Find leftmost target plus 1, subtract 1, validate. Got it. What's the second method the source mentions?
Method 2 also involves transforming the search target, but this time using a non-integer value, assuming your array holds integers, of course.
Like searching for a decimal.
Exactly. The idea is to pick a value guaranteed not to be in the array. So for the leftmost target, this method suggests you could use your binary insertion function to look for target 0.5.
Target 0.5. How does that help find the leftmost target?
Well, think about where target 0.5 would fit. It's smaller than any target, but it's bigger than any integer strictly less than target.
Okay.
So in a sorted array of integers, the correct insertion point for target 0.5 will be immediately before the first actual target.
So the index I returned by the insertion search for target 0.5 is the index of the leftmost target directly.
That's the claim. You use this fractional value to make the insertion point land exactly where you want it.
Okay, that's interesting. And for the rightmost target using this decimal approach?
You follow the pattern, search for target plus 0.5.
Let me guess. Target plus 0.5 is bigger than any target, but smaller than the next integer value up.
Precisely.
So its insertion point index I would be the position of the first element that's strictly greater than target.
Exactly. And just like in method 1, target plus 1, the element right before that at index j equals I1 must be the rightmost target.
So method 2, for leftmost, search insertion point of target 0.5 and return I. For rightmost, search insertion point of target plus 0.5, return I1.
That's the essence of it.
Does this avoid the validation checks we needed before?
Largely, yes, because you're searching for values, target 0.5, target plus 0.5, that you know won't match any integer element. The insertion point itself gives you the boundary information more directly.
Are there any catches?
Well, the source notes it assumes your array doesn't contain decimals itself, and depending on the programming language, you might need to handle the search value as a float, maybe do a cast, though languages like Python are often flexible here.
Okay, so two quite different, but conceptually related ways to find the right boundary, both circling back to using binary search insertion. Method 1 uses target plus 1. Method 2 uses target plus 0.5.
Exactly. Both are about cleverly transforming the problem.
So let's try to synthesize this. We've explored how to find both the first and last instances of a value in a sorted array, even with duplicates. And the key theme from Hello Algo seems to be leveraging the binary search insertion concept.
Right. Finding the left boundary maps almost directly to finding the insertion point for the target value itself. Just need those couple of validation steps.
And finding the right boundary involves a transformation. Either find the insertion point for target plus 1 and look at the index before it, or find the insertion point for target plus zero point 0.5 and look at the index before it.
It really showcases a powerful idea in algorithms, problem reduction, seeing how a new problem relates to one you already know how to solve.
It does make you wonder, for the right boundary, which method is better? Target plus 1 or target plus zero point 0.5? The source didn't seem to pick a winner.
No, and I suspect it depends. Maybe on the robustness of your insertion function, your data types, performance nuances, or even just which one feels more readable or intuitive to you and your team.
Context matters, as always.
Indeed.
So we've taken this deep dive into the Hello Algo perspective on binary search boundaries. You've learned how finding the leftmost position connects directly to the insertion point idea.
And you've seen two distinct, pretty clever ways to find the rightmost position by tweaking the value you search for using either target plus 1 or target plus zero point 0.5.
The core idea is really about building on existing binary search logic, not reinventing the wheel for boundary cases.
That pattern reducing one problem to another is just such a valuable technique to have in your algorithmic toolbox. It makes complex problems feel more manageable.
Definitely. So here's a final thought for you to consider building on this. We saw this clear link between the left boundary and inserting target, and the right boundary involving inserting something just beyond target, target plus 1 or target plus zero point 0.5. What does this underlying relationship between boundary finding and insertion point location tell us, perhaps more generally, about how we define and locate ranges within sorted data using binary search?
And maybe think practically, too. How could the specific ways your chosen binary search and insertion function handles edge cases like empty arrays or arrays where all elements are the same? How might those implementation details ripple through and affect the correctness or even the performance of these boundary finding methods we discussed? Something to chew on.